Thank you again for giving me the opportunity to present my recent work in Quantum Science Test 2023. And my work is on quantum speed limits. And I am currently based in Korea Institute of Science and Technology in Seoul, South Korea, and as a postdoc. And now I go to the main part of my talk. So at first I say what is the plan of the talk. And also I would like to first mention the collaborators with whom I have worked on this topic. And there is a graduate student of Srivastav in India in Harishchandra Research Institute. And there is Dimpi Thakuria, who was in India at Harishchandra Research Institute, but now in Vienna pursuing her PhD. And of course, Professor Arun Kumar Pati, who was a professor at Harishchandra Research Institute, but is now currently based, he is a professor now at International Institute of Information Technology in Hyderabad. So all of the works have been done in collaboration with them. So in the plan of the talk, at first, I talk about the motivation, why we will study the quantum speed limits. Then I'll go to the background one, which is on time-energy uncertainty relations. The background 2 is on quantum speed limit. The background 3 is on tighter uncertainty relation for pure quantum states. Then I'll go to the main part of my talk, which is the results. That includes the tighter uncertainty relations for mixed quantum states, tighter quantum speed limit for pure quantum states, tighter quantum speed limit for mixed quantum states. Then I'll mention some examples of these tighter quantum speed limits. And then I'll go to the result 4, which is stronger quantum speed limit for mixed quantum states. And I'll give an example there. And at the end, I'll go to the future directions. So the motivation. First of all, it has a fundamental importance. It was shown by Mandelstam and Tam that the correct interpretation of the energy-time uncertainty relation is as a bound on the evolution time of a quantum system. So it arose as a need to explain the time-energy uncertainty relation, because time is not in the position of an operator in quantum mechanics. So one had to develop other interpretation for the delta T involved in the time-energy uncertainty relation, and it came as, and all the explanations were given using the quantum speed limit concept. Not only this, there are practical applications. The quantum speed limit bounds have proven to be very useful in quantifying the maximal rate of quantum entropy production, the maximal rate of quantum information processing, and quantum computation. So there have been many works on this, and I can give you the references later, and it's if you want. And there are other practical applications, like quantum speed limits have also found a wide range of applications in optimal control theory and quantum thermometry as well. So we see that we have both the fundamental importance as well as practical applications. And as a result, these motivate us to find better quantum speed limit bounds that can go beyond the standard quantum speed limit bound, such as the MT bound, and find several applications in the aforementioned areas. So first, I go to the background 1, which is the time-energy uncertainty relations. The uncertainty principle and the uncertainty relations are of central importance in quantum mechanics. The uncertainty relations have helped us to reveal the behavior of the microscopic world in many different ways. The uncertain relations are also capable of capturing the intrinsic restrictions in the preparation of quantum systems. And these type of uncertainty relations are called the preparation uncertainty relations. This interpretation was quite fruitful for the uncertainty relations like position momentum and the angular position angular momentum uncertainty relations. However, the energy time uncertainty relation is different from the above stated uncertainty relations because time is not treated as an operator in quantum mechanics, but as a classical parameter with no inherent quantum uncertainty. So, time not being a quantum observable in the standard quantum mechanics, energy time uncertainty relation lacked a good interpretation as such, like for those of the other quantum mechanical observables like position and momentum. It was shown by Mandelstam and Tam that the correct interpretation of the time-energy uncertainty relation is as a bound on the evolution time of a quantum system, now known as the empty bound or the quantum speed limit bound. So, therefore, a natural extension and consequence of the time-energy uncertainty relation in quantum mechanics is the derivation of the so-called quantum speed limit. Okay, so now I go on to the background for quantum speed limit. Quantum speed limit is a fundamental limitation on the speed of the evolution of a quantum system imposed by the laws of quantum mechanics. Historically, Mandelstam and Tam derived the first expression of the quantum speed limit time as this tau QSL, which is given by pi by 2 delta H, where the initial and final states are orthogonal. And H corresponds to the Hamiltonian, which evolves the quantum system, and delta H corresponds to the variance of that. The QSL can be generalized for the evolution between two non-orthogonal states as well. And so it involves a quantity S0, which gives an overlap between the quantum state psi at time t to psi at the initial time. And tau QSL, as stated just above, is the celebrated empty bound and gives the minimum time required for a quantum system to evolve between any two states unitarily. So now in our work, we have used a certain type of uncertainty relation called the tighter uncertainty relation to improve on the previous quantum speed limit bounds. However, the tighter uncertainty relations only existed for pure quantum states, which I'm going to review here. So for any two generally non-commuting operators, A and B, the Robertson-Schrodinger uncertainty relation is, we know, the very well-known form, which is given in the slide. And however, this uncertainty bound is not optimal and not the tightest one. And there have been several attempts to improve the Robertson-Schrodinger uncertainty relation bound, for example, by McConney and Patti, and by several others later. And in our paper by Dr. Mondal and Professor Patti, we have derived a tighter version of the uncertainty relation for pure quantum states, and the mathematical form is given in the slide. And it involves various mathematical quantities, but they are very simple to define. And this is the exact form that we will use to derive the tighter uncertainty relation for mixed quantum states, and then use it for quantum speed limit bounds for mixed all general quantum states. So now I go on to the next slides. First, we mentioned that we derive the tighter uncertainty relation for mixed quantum states. And I, of course, will not go to the details how we derive it, but I just state what is the expression for the tighter uncertainty relation for the mixed quantum state. And it is given by this delta A, delta B into delta B, and it's in the product form. So there are various quantities involved in there, and the rho is the mixed states in which we are deriving the tighter uncertainty relation for. And And there we can also optimize over this tighter uncertainty relation for mixed quantum states over the choice of our basis, which defines this particular set of psi n, okay? So there are two steps, and for all this holds for any psi n, but we can also optimize it over all sets of psi n to get a better bound. Now we derive the quantum speed limit for pure quantum states from tighter uncertainty relation. So the statement is that the time evolution of a quantum state under a unitary operation generated by a Hamiltonian H is bounded by the following inequality. So we see that there the first term is exactly the empty bound, okay? And then we have an extra term on the right, and it's we add this term to the empty bound. And the various quantities, what are defined is this A0, which is exactly what it was defined as for the empty bound. And there is a variance of H, and there is another term KT, which is dependent on this quantity psi n as something new. And we have proved that this quantity KT is always greater than equal to 0. And also, not only this, for the interval of time that we have chosen, this integral on the right is mostly positive, okay? So next I go to the quantum speed limit for pure quantum states from tighter uncertainty relations, a few steps for this. So we take A to be the pure quantum states psi 0 projector, and A0 is defined by this inner product between psi 0 and psi t, as you can see in the slide. And we use the relation that delta A into delta B greater than equal to half of expectation value of the commutator between A and B plus KT. So this is the tighter uncertainty relation for pure quantum states. And we use Ehrenfest theorem and some trigonometric parametrization. And we obtain the final equation, which defines our speed limit from tighter uncertainty relation for pure quantum states, which is given in the last line of the slide. Okay, so now we go on to the tighter quantum speed limit for mixed quantum states. So in the previous slides, you have seen that the tighter speed limit for pure quantum states has an empty bound term plus a positive quantity, and then plus a quantity which has a term which is always positive. And so the separation between the previous bound and the previous empty bound and this bound is very clear to see from there. And it's very clear to see from there that whenever this integrand on the right for this pure quantum states is zero, is positive, we always have a bound which is better than the empty bound for pure quantum states. And but however, we want to generalize that quantum speed limit bound for mixed quantum states, and we arrive at a solution which takes the form as you can see in the slide. In this slide, given by this tau greater than or equal to a quantity on the right-hand side. And as before, it can be maximized over all possible sets of psi n, and which again has a quantity which is KT, a generalization of KT of the pure quantum states to mixed quantum states. And we have proved that this quantity KT is always positive as well for mixed quantum states. So the definition of A0 is now a little bit different, but this is definition of A0 reduces to the previous definition of A0 if we replace rho 0 and rho t by pure quantum states. So this is the new bound that we have derived, and it doesn't resemble any of the earlier bounds for quantum speed limit for mixed quantum states, which is an active area of research even today. And so as a result, we cannot directly analytically prove that this bound is better than all the previous bounds for quantum speed limit for mixed quantum states. So we take a number of different examples and show that in all of these cases, our bounds always perform better than the empty-like bound for mixed quantum states as well. So example 1, I'll just show some plots here. The random Hamiltonian example, we take some random Hamiltonian from the Gaussian unitary ensembles. These are all valid Hamiltonians with all the desired properties for the Hamiltonian. And we take, for example, an initial pure state, and we choose some random eigenbases, psi n, and we plot the term delta tau tighter quantum speed limit hour bound and the empty bound for pure quantum states in this example. And we have plotted this difference, and you can see in the left-hand side for all the time, starting from the initial point to all the time that we have plotted here. This difference is always positive, which shows that our bound performs better than the empty bound for pure quantum states. Now we go to another example, which is an interacting quantum system of spins. So now we have an internal Hamiltonian as well as an interacting part Hamiltonian, which contains the interaction part. So there is interaction between adjacent spins in this model of the Hamiltonian. And we start from a product state, psi 0, and we evolve under this Hamiltonian of interacting spins. And it's a spin chain which are interacting among each other. And we plot again the difference, tau to TQSL minus tau MT. And we also show that the difference is even big, always positive, showing that our bound performs better than the empty bound for pure quantum states. So I gave an example there, but now I will go to the stronger quantum speed limit for mixed quantum states. So we have proved in the previous slides, we showed that we have proved a tighter quantum speed limit for mixed quantum states and showed some examples where that bound performs better than the previous bound, but it's not guaranteed analytically that it is the best bound or the most optimal one. So we try to find other bounds which can perform better as well. So for that reason, we derive the stronger quantum speed limit for mixed quantum states, and and it's all for unitary evolution generated by a Hamiltonian. And you can see the form of this bound in the slide here in the first equation. The definition of A0 remains the same as before, and also delta H, but we have a different quantity which is called RT here, which is dependent on an operator sigma, which has to satisfy some properties given in the last line, which is trace of rho to the power half and sigma equal to 0, and this norm of these operators has to be 1, and the definition of the norm is given in terms of this En, where they form a complete orthonormal basis. So this is another bound that we derive, and I show with an example here that we actually have a lot of different examples, more than like 5 or 6, but I just show as an example, just one single example that we compared with three different bounds, important bounds which exist in the literature. And we found that our bound always performs better from those bounds for mixed quantum states. And the example is here given for these 2 important bounds, which were published in physical review letters before. And we have just done optimization of 5 random Hamiltonian operators, say, of this operators sigma, and we always see that our bound performs better than the previous bounds.
I'm very, very sorry. Sorry for interruption,
yeah.
but we have no time. So
yeah, I think this is just the last slide, almost the last slide. Thank you. So this is perfect. Okay.
We have 2 questions. The first one is concerning the basis. Sorry?
I have just one more slide, so I'll finish.
Oh, so. Okay.
So there are some future directions. It remains a subject of future investigation to compare our bound with the Margulis-Levitin bound, where empty bound is weaker than the Margulis-Levitin bound. It will also be interesting to see how speed limit bounds can be improved by optimization over different choices of sets of orthonormal bases, and which basis set will be optimal one in deriving the optimal quantum speed limit bound. We can also generalize tighter quantum speed limit bound to the case of mixed quantum states for open system dynamics. And we believe that the tighter quantum speed limit derived here will have important application in quantum computation, quantum information, and quantum control. And our works are already in the open access, like it's under peer review, but they're in the preprint form in archive and in preprint. And we have some acknowledgements, and thank you. That summarizes my results. Thank you.
Thank you very much for very, very nice talk. Thank you. Sorry for interrupting. We have restrictions. We have time restrictions, so we have to finish in time all the talks. So very short answer on the question: can these 2 terms have correspondence with the 2 terms in slide 11 with uncomplexity corresponding to the kinetic and potential energy components? So you can see this question in chat.
Okay. Actually, I don't exactly remember the expressions in the, as he's saying, like I have to exactly remember the mathematical terms. Maybe we can discuss this later. Perhaps there could be, but often I cannot exactly comment on that. So if I knew those terms properly, I would have been able to comment.
Thank you. And the last one, so can you please share your paper, maybe in the chat?
Yes. In the chat, I can, in my slides, I have given the link for the archive and the preprint, but in the chat also, I'll give that. Yeah.
Okay. Thank you so much for the nice talk. Thank you.